Okay, hello and welcome everyone. So this video I'm going to call Simple Games Part 2, and it's basically solving this game by seeking best responses to find a Nash equilibrium. I'd written this up, it's a little bit wordy, I'll read through it. Hopefully it's still useful, I don't know. I had written this for another purpose, and I was like, oh, wait a second, somebody might find this useful, and if that's you, that's what this is for. So anyway, here we've got this matrix, and we want to find Nash equilibria. Now we define Nash equilibria as occurring when all players are selecting strategies that are best responses. So no one wants to unilaterally deviate from their strategy. So here I've got two players. I've got row player who can select high or who can select low, column player who can select near or who can select far. And I've got their payoffs in the table. You can think of these as like utility values, like well-being that happens as a result of the combination of strategies for the players. You can think of it as like money or something. The first number goes to row player. I made them odd so that the odd numbers are always going to row player. The second number goes to column player. I made them even, so the even numbers always go to column player. All right, so I want to solve by finding best responses. Maybe you could stop the video and try to do this first on your own, and then I'll walk through it. And then I'll do this by the underline method. But first, what I'm going to do is I wrote this out verbally, so you can follow my logic as I'm talking about this. Basically, what's happening here is we have the convention for most normal form games, unless stated otherwise, that players are choosing their strategies at the same time, simultaneous, meaning they don't know what the other player has done, but they know what they could do. And so they see these payoffs, they see the possible strategies. And so what we're going to do is we're going to say, okay, well, hypothetically, if we knew what the other player was going to do, what would we optimally choose? So that's what we do to find best responses and to find Nash equilibria. So I'm going to say, if I'm row player, column player has selected near, hypothetically, how do I best respond? Well, if I select high, I get 9. If I select low, I get 7. So if column selects near, row player best responds by selecting high, because 9 is better than 7. If column player selects far, row player also best responds by selecting high, because 5 is bigger than 3. Right? So if column selects far, row player's best response is to select high. If they selected low, they get 3, but they want that 5. Now we turn it over and we look at from the perspective of column player. So if row player has selected high, what does column player want to do? Well, if we're in the top row, column player could either get an 8 by selecting near or 4 if they select far. They'd rather have 8, so they're going to select near. So column player's best response to row's choice of high is near. What if row player selects low? Well, column could play near and get 6 or far and get 2. They'd rather have 6. So again, they're going to best respond by selecting near. If row player selects low, column player's best response is to select near. So I can also do this by underlining those best responses. If you do this by like the underline method, right, this is what this will look like. If you have two underlines in the same column for column player, that gives us a dominant strategy for column player. If you have two underlines in the same row for row player, that gives them a dominant strategy. If you have two underlines in the same cell, that gives us a Nash equilibrium. So there's a single Nash equilibrium, high and near. Both players have a dominant strategy, just mentioned that. It's high for row player, for column it's near. We know high is a dominant strategy for row because regardless of what column does, row is going to want to play high. And near is a dominant strategy for column because it doesn't matter what row does. Column always does better with near, does better than far. Remember, dominant strategies don't like win the game or like outdo your opponent. No. Dominant strategies dominate your own other alternatives, right? So high dominates low for row player and near dominates far for column player. Right? That's what's going on here. This is not a prisoner's dilemma though. Interestingly, looks like one, but it's not. Look closely. They both have a dominant strategy. That's one of the criteria for a prisoner's dilemma. The other one is we have to have a misalignment of group and social incentives. And that happens by seeing if your payoffs when you play your non-dominant strategy exceed if the sum of your payoffs when players play their non-dominant strategy exceeds the sum of their payoffs when they play their dominant strategies, then we got a social dilemma, a prisoner's dilemma, right? That doesn't happen here. So we can see this by summing up their payoffs. Actually, their jointly highest payoff, like the sum of values that player, that column and row player are getting is the highest when they play their dominant strategy, right? So it's 9 plus 8. That's bigger than 3 plus 5. Actually, when they play their dominant strategy, right, their joint payoffs are minimized. And then here it's 13, here it's 9, right? So this is not a prisoner's dilemma because it's not a social dilemma. Actually, individual and group incentives are both driving them towards near and high. So in other words, like, this should be a pretty stable equilibrium because both their individual incentives and any type of group incentives are all aligned. It's all pointed in the same direction where they want to get this. They want to get that 9 and the 8. The high and near equilibrium is individually beneficial, and it's also individually optimal, and then also maximizes social surplus. Note that doesn't always have to happen. So in Nash equilibria, doesn't say anything. The way that I mentioned at the outset didn't have anything to do with maximizing payoffs, right? Didn't have anything to do maximizing payoffs. Nash equilibria is just all players are best responding. In the prisoner's dilemma, actually, Nash equilibria will typically give you the minimum joint payoffs, right? And that can happen in a lot of other games. So Nash equilibria just means everybody's best responding. Didn't say anything about maximizing payoffs or anything like that. Although sometimes that might happen, such as in this game here. Anyway, so I'll go ahead and conclude. Hope you enjoyed the video. I'll link up some other videos that might be useful. See you next time.